What up, pre-calculus students? Mr. Messner. Let's go. This is not that long of homework. Find the zeros of the function. Zeros of the function, when a function equals 0, how do you get 0 in a fraction if these are rationals? So 0. As long as you have 0 in a numerator, 0 divided by anything is 0, except 0. 0 over 0 is undefined. We'll talk about what happens with that situation a little bit further, maybe next class, maybe this class. So keep in mind that if you get a 0 in the numerator, it's not going to be a 0 if you have a 0 in the denominator. We'll talk about what happens. So all I need to do is see when the numerator equals 0. Remember, numbers over 0, those are also undefined, but these are indications of asymptotes. These are indications of wholes. We talked about during the last homework video that it's like a number divided by something getting closer and closer and closer to 0 gets bigger and bigger and bigger and bigger. So going up towards infinity, but you can't plug in the value to get 0. You can't divide by 0. Anyways, give 4 and -1. That's easy. My cursor is bugging out on me again today. Here, we can factor the numerators set equal to, and solve set equal to 0. X minus 2, x minus 1. 2 and 1. Wait, not 1. X equals 1 as a whole. X equals 2 is a 0. Now, let me show you why, okay? I'm going to show you why that's a whole. So, let's just look at the factored form. X minus 2 times x minus 1 over x minus 1. Well, what I notice is, like, if I plug in any value into this, like let's plug in 5. 5 minus 2 is 3. This would be 4. This would be 4. So it's 5 times 4 divided by 4. Well, that's just 5, right? Because the 4 divided by 4 cancels. Okay, if I plug in 2, well, I get 0 times 1 over 1. Okay, well, that's just 0. This doesn't make any difference. If I plug in like 1.5, I get -0.5 plus 0.5, or -0.5 times 0.5 over 0.5. Well, the halves cancel, and again, just get the -0.5. What happens is that these will essentially just cancel each other out, and you're going to be thinking, oh, my function is x minus 2. Okay, so this is the same as x minus 2? Almost. It's almost the same as x minus 2. Like, I'll show you. And this might be the right time to do this, and this might not be. This is like part of your notes and stuff. So we have x squared minus 3x plus 2 over x minus 1. X squared minus 3x plus 2. Okay, look. This is the exact same as x minus 2. They're right on top of each other. I don't know why I put x. Okay, but there's one difference. X is 1. Let's zoom in when x is 1. Let's get rid of this. Let's look at x equals 1. It looks like it's going to be -1, right? No. It's 1 comma undefined. Why? Because I can't plug in 1 because I'm not allowed to divide by 0, especially 0 divided by 0. It's just not allowed. Okay? Now, what we find is that the simplified version will be able to tell us where this hole is located. So the y equals x minus 2, this has the point 1, -1, versus this one doesn't. So we have a hole. The graph looks like the other graph, but it's not a 0. It's not an asymptote. It's an interesting thing. So going back to my answers, I'm sure you guys just want to get to the answers right away. You don't really care about this. So this is like almost the exact same thing as x minus 2 with one exception. When x is 1, this has a hole. X minus 2 doesn't have a hole. All right, so x equals, what was this? X minus 2, x minus 1. X equals 2 is a 0. X equals 1 is a hole. All right. Let's factor out x. X squared plus 4x minus 32. Since I factored out an x, there is a 0 at 0. If I plug in 0 here times this is 0. Everybody's still making mistakes on like this is x factored out. I need 0. If I just factor out a number, 0 is not a solution now. Okay, like it's the fact that when I plug in 0 here, 0 times anything 0. Let's factor this. 8 and 4, positive 8, negative 4. So 0, negative 8, positive 4. Y-intercept. Y-intercept is when x is 0. Okay, when you're looking at a graph, when x is 0, you're going to hit the y-axis somewhere. So plug in 0 for x. Let's get the y. Negative 4 times 1 over negative 5 times 2. Negative 4, negative tenths, which is 2/5. F of 0. Do I have to factor this? Nope. It's just find the y-intercept. 2 over negative 1. Negative 2. F of 0. Negative 12 over 6. Negative 2. I wonder if they want you to find the zeros of these as well. But they didn't ask me for it. Vertical asymptotes. Vertical asymptote. Talked about last class, talked about today. If you have a number divided by 0, that is an indication that we are talking about a vertical asymptote. Now, you're not allowed to divide by 0, but think about it. If you have like 5 over something getting closer and closer to 0, so like 0.1, this is 50, 500, 5,000, 50,000, keeps going, keeps going. So the closer and closer I get to 0, the larger and larger this comes. So what we're talking about is like, I don't know, maybe this occurs like somewhere. If I get closer and closer to infinity, I will eventually get to I will never reach something. Like what happens is as we plug in a value, the denominator will get closer and closer to 0, but you still can't plug in this value. This is why we like trend up towards infinity, down towards negative infinity, but we can't cross this line because you're not allowed to plug in that value. You also might not go positive, negative infinity. You might just be like positive infinity on one side, positive infinity on the other side, or negative infinity on one side, negative infinity on the other side. Anyways, all you guys care about is the answers, which are when the denominator equals 0. So set the bottom equal to 0. I got 2 pieces of a product that we can solve. This piece, when I either factor, which you don't want to do because you'll have roots. I mean, you could. It's x plus root 3, x minus root 3. Here you just kind of, since it's just x's, move this other stuff to the other side. There's not x squareds and x's. It's just like one set of x's. Square root to solve, I get plus or minus x equals 3, x equals root 3, x equals plus or minus root 3. Over here, you get square root both sides. You get plus or minus 0, but that's just 0. So you just end up taking the inside and setting it equal to 0. Solving. Okay, so 3. This guy, take the denominator, set it equal to 0. 2 numbers that multiply to get 63 and add to get 2. 9 and 7. I was just using my fingers there. 9 and 7, 63, 63. Okay, so x minus 7 over x plus 9, x minus 7. Whoa, careful, careful. If I said -9 and +7, I would be wrong because -9, indication of a vertical asymptote, because you have a number, -9 minus 7 is, sorry, yeah, -9 minus 7 is a number divided by 0. You can't do, but again, you're going to get close to that number divided by something close to 0, going up to infinity, down to negative infinity. 7 is a whole. This function would look just like 1 over x plus 9, except the original function, the x minus 7 function, is as a whole, where 1 over x plus 9 does not have a whole. 5 over x plus 2, x equals -2. Asymptote. Horizontal asymptotes. A lot of different ways to teach this stuff. How I teach it is like, it's all about fastest growing terms. Okay. If I plug in very, very large values, like over here, like very, very large values into x cubed, x squared, and 2x, what I tell my students is that you can actually just ignore the slower growing terms. And just like forget about them. And this function, when we're talking about, and horizontal asymptotes is when we're looking like what's going on all the way over here to the right, all the way over here to the left. Okay? If I'm looking at the infinities, plugging in really, really large numbers here, I can cross off those. I'm going to show you a quick example because it's important, and like I always like to do it in my calculus classes. I'm going to my friend. Let's like take x cubed and x squared. Okay, let's say like I have some function x cubed plus x squared. I'm telling you, cross off the x squared, it won't mean anything. Okay, what do I mean by that? It's like, well, if you can divide two numbers, you can see how much larger one thing is compared to the other. Okay, so like x cubed divided by x squared. We could look at the graph of this and see like how much bigger is x cubed compared to x squared. But it's going to be tough to see it on a graph when we talk about big numbers. So what I'm going to do is plug some numbers in for x and compare like how many times bigger is x cubed over x squared. All right, so let's plug in like 100. 100 cubed over 100 squared. Obviously, you're going to get the answer is like, oh, it's 100 times bigger. Now, what does that tell you? 100 times bigger is almost like when you're adding the two numbers, you are adding something that's 1/100th of the size to something else. Okay, now that's still changing the numbers. Like 100 cubed is that, and then if I add 100 squared, like I changed the third decimal place. That's really changed. It seems like it's really changed the number. Well, watch what if I plug in something like a big number like 100 to the 100th. 100 to the 100th is now we're talking about like a bigger number. I think like 10 to the 100th is a Google or something like that. So let's talk about 100 to the 100th. Well, like if you did the math, you can figure out like you would see this is how many times bigger 100 to the 100th cubed is compared to 100 squared. Okay. Now let's watch this. I'm going to cut these out. This number cubed is this number. So 10 to the 100th cubed is this one followed by this many zeros. Now watch. If I add this number, let's see where the change happens. Right here. Okay? Now let's think about this. We've gone this many zeros, and then we change this number. Are we significantly changing things? No. What you can compare this, like changing this, is like taking 1 and adding this many zeros followed by a 1 to 1. Are you changing what you have? Not really anymore. It's barely making a nudge. So this is why I say, like, actually ignore this stuff. Okay. Now, what do? Now, I'm not using Bob Yo, Bot No. That's like something you memorize rather than something you kind of understand. I say, well, if you have x squared over x, well, can you simplify that? Yeah, I can. That's just x. Now you gotta look both in both directions. You gotta look at what's going on to the right and what's going on to the left. Well, let's think about it. If I plug in infinity into x, what do I get? I get infinity. Okay, so that's what's happening. If I plug in negative infinity into x, what do I get? Negative infinity. Okay, let's see what happens here. Well, this goes, this goes, this goes. Those are insignificant compared to just x over x squared. And when I simplify this, I get 1 over x. Okay, well, if I'm plugging in large values into the denominator here, like 1 over, okay, just like keep adding zeros. What happens? Well, it's like we're going to get a fraction that keeps getting smaller and smaller and smaller and smaller and smaller. What's it going to approach? 0. Now, what if I plug in a very large negative number in for x? Well, it's going to be negative, but it's still going to approach 0. And we don't like to like say 0 is positive or negative. I could say it's like 0 from the left, and you'll learn about that in the in calculus land, which means it's like just to the left of 0. It's like a negative value, but close to 0. So that'd be it. Now let's look at this. Again, like the 19x, the 12, the x squared, the 2x, they're insignificant when we're adding things together. They're like adding very, very, very small decimals to very, very large numbers. We can just look at 5x cubed over x cubed. What happens? That just simplifies to 5. Well, if you plug in infinity into 5, you just get 5 because there's nothing to plug in. Like what essentially happens is the growths of the x's cancel, just leaving you with that leading coefficient. I don't know if that's eats DC or something like that. I don't know. So I just go pew, 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 pew. And I can just say plus or minus infinity gives us 5. Same thing here, plus or minus infinity gives us 0. Holes, there we go. Now we got holes. Okay, 0 over 0 is an indication of a hole. We're going to be using another function, except for this one point. And when this one point, boom, you got a hole. You can use the other function to find the location of the hole. I'm going to factor the top and bottom, and I'm going to see whenever I have a 0 on the top and a 0 on the bottom. That's a hole. We do this in calculus. We find holes, and we find asymptotes and stuff like this. So this is good prep for calculus. This is how I teach it. X equals -3 is an indication of a hole. Now, where's the location of the hole? What you'll find is like cross this out, plug in -3 into like the simplified function that doesn't have the hole, but acts just like the original function, and you get -1/2. We'll figure that out, I think, next class. Actually, they want you to find the coordinates. So here we go. The coordinates would be the location. Okay, cool. So x equals -3 is the hole, but what is the location? Well, like this, I don't want to say equals, but it's pretty much the same. This first equation is pretty much the same as x plus 2 over 2, except this equation, they share this, all the same points, except this equation you can plug in -3 into. This equation you can't because you get 0 over 0. So the location would be like plugging in -3 into my simplified equation that mimics the first one, doesn't have the hole, gets -1/2. That'll come back soon. All right, let's look at, that might be it. Maybe this works now. This guy, 4 things we're probably going to factor by grouping. Factor out an x squared, x minus 2. Pretend like I'm factoring out of 1. The numerator becomes x minus 2 after that's factored out, and x squared plus 1. That's over x minus 2. Okay, now this is my function. I can see that I get 0 over 0 if I have x equals 2. I know that this is going to pretty much be the same as x squared plus 1, except for x equaling 2. At 2, this is telling me that this function's got the point 2,5. This function has a hole at x equals 2. I will show you. I'll go back to Desmos, actually. So the location using x squared plus 1 is 5. So 2 comma 5. Ready? Go back to Desmos. So I got this big function, x cubed minus 2x squared plus x plus 2, x minus 2 over x minus 2. Okay, there it is. Now watch this. At x equals 2, at 5, oh, no, it's not 2, 5. I can see where the location is. Location's at 5, but Desmos is telling me at 2 we are undefined, which is correct because you get 0 over 0. But if you look at x squared plus 1 equals, graph for me. You see it's right on top of the first graph, only this does have the point 2,5. So I can plug in 2 into this. There's not going to be any holes here. I know that. Why? Because you can't get 0 over 0. So no holes. Let's find the asymptotes, though, for fun, because this is the last problem. Incredible. Factor out an x squared minus 2x plus 1. That's x minus 1 squared. So 1 over x squared, x minus 1 squared, x equals 0, comma 1 are vertical asymptotes. Notice the multiplicity of these. What you'll find is that you won't change signs at the vertical asymptote. You'll essentially like bounce or say at the same sign. We can see that if we graph, but we could also see that if we did a sign analysis. It's the fourth minus 2x cubed plus x squared. So at 0, we stay in positive land. Oh, look at that. Then we bounce off at 1. Where's 1? 1's like over here. Then we come back to positive land after 1. So there's like another asymptote up here. It's tough to see, but this is an interesting graph. Like we go up to infinity at 0. We come back from infinity after 0. We go up to infinity before 1. We come back from infinity, keeping the same sign. There are no negatives for this. All right, good stuff. Precalculus.